All right, mathletes, so this is chapter 2, C and D, scientific notation and rational indices. So scientific notation is really good when we're trying to explain very large numbers, like the number of cells in the human body. Very large number. So here we're talking hundreds, thousands, millions, billions, trillions. So if we want to represent trillions without writing all those zeros, it's nice to use scientific notation. And it's also useful for writing very small numbers, such as the number of the number of grams of chlorine in a glass of water. So very small numbers. It gives us some kind of perspective based upon the power of tens, how big or how small that number is. Okay, so scientific notation should always be of the form a times 10 to the k, where a must be a number between 1 and 10. It could be 1 inclusive, but it shouldn't be larger than 10. And where k is always a integer, when it's a very large number, okay, k is positive. And when a very small number, like the number of grams of chlorine in a glass of water, k is negative. And we'll look at some examples with that. So, example 1 here. So, if we're trying to represent this number, 4.5 million as a scientific notation, I'm going to recognize the number that I want to look at is going to be 4.5 because that number is between 1 and 10. Well, 4.5 times what power of 10 will give me this 4.5 million. So I count, if my decimal place is here, I can count over 1, 2, 3, 4, 5, 6. And 6 decimal places is 10. You can imagine multiplying by 10 each time, and we know if we do like 4.5 times 10, that's equal to 45. So how many times, and that's just moving this decimal place over 1. So how many times do we have to move that decimal place? Well, it's going to be 6. So 4.5 times 10 to the 6 is that. Okay, so now, similarly, when we're thinking about a really small number, like in example 2, okay, I truncate it and I look for what number here is going to be between 1 and 10. So if I put the decimal place after the 5, I get 5.92. So that number is between 1 and 10 times 10. Well, we need to do negative powers. So we remember like 10 to the negative first is equal to 1 over 10. Okay, so we're dividing by 10. And so if we had a number like 77 and we divide it by 10, well, that's just 7.7. We have moved this decimal place now to the left. Okay, so in this procedure, as we're looking at it, we're going to move it over 1, 2, 3, 4 places, and that's going to be negative 4. So 5.92 times negative 4 is that very small number. Notice negative power here for small numbers and a positive power there for large numbers. Let's look at our next example. Okay, so now if we want to go the other way and we want to write it as an ordinary number, okay, we are going to write 3.2 times 10 to the second. Well, I know that I'm going to have to write as 3.2. I'm going to have to move my decimal places to the right because it's a positive number, so it's going to be larger than 3.2. So to make 3.2 larger, I'm going to move it once, twice. So my decimal will go here. I'm going to fill in that back area with zeros. So really, this is equal to 320. Okay. Now, in example B here, part of 3, I'm negative 5. So as I'm thinking about 5.76, I'm going to move my decimal place 5 times, but I'm going to move it to the left because I want a smaller number. So I'm going to go 1, 2, 3, 4, 5. So my decimal place would go there, and I'm going to add a 0 there, 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 and there. So I can see that 5.76 times 10 to the negative 10th, negative fifth is going to be, I'm going to do 0 point, so I have 4 zeros, 1, 2, 3, 4, 5, 7, 6. And again, recognize that a negative exponent gives me a very small number. All right, moving forward to example 4 and 5. So as we're doing our multiplication and division of scientific notation, we can break things down into their parts that might be easier. So if we have 5 times 4 times 5 times 10 to the 4th times 4 times 10 to the 5th, I'm going to group my integers together and do 5 times 4. And then I'm also going to group my powers of 10 together. 10 times 4 times 10 to the 5th. Okay? And I'm going to simplify that. 5 times 4 is 20. And 10 to the 4th times 10 to the 5th is going to be 10 to the 9th. Remember our laws of exponents, that this is just coming from 4 plus 5. Okay? So if we have this here, we've multiplied it, but the problem is this 20 is not between 1 and 10. So I need to account for that. So I'm going to write this so I know that I can write this as a power, 2, what times powers of 10 can get me? 20, and it's going to be 2 times 10. Okay, I'm going to put a 1 there. Just as I'm using my laws of exponents, I know I have times 10 to the 9th. So now that I have powers of 10, I'm going to combine these again. And I'm going to see I'm going to get 2 times 10 to the 1 plus 9 is 10. Okay? And just by looking at this, I can see that this number is larger than these other numbers, okay, because of the power of 10. Okay? So now with division, I'm going to do a similar type process. So I'm going to group my 8 and 2 together. So I got 8 divided by 2. And then I'm also going to group my powers of 10 together. So I have 10 to the 5th divided by 10 to the 3rd. Okay? Well, now I simplify 8 divided by 2 is going to be 4, and 10 to the 5th divided by 10 to the 3rd. So my laws of exponents say that I do 5 minus 3, and I'm going to get 10, and 5 minus 3 is 2. At this point, I recognize that 4 is between 1 and 10, so I'm done there, and I get that number. Okay. Notice that 10 to the 2nd, 4 times 10 to the 2nd is smaller than the power of 10 to the 3rd, 10 to the 5th, which should make sense that when we're dividing numbers, we're going to end up getting something smaller as long as those numbers are larger than 1. All right, let's look at some other examples here. And we're jumping into rational indices. So the big idea is that a rational number is a number that can be expressed as a fraction, okay, where we can't be dividing by 0. So if we have a power that is rational, we can also write it in the square root form, where n to the square root a is called the nth root of a. Okay, so let's look at a couple basic examples. So 16 to the 1/2 power can also be written as a square root of 16 second power. And remember, our default, if it's a square root of 2, we can just write it as this. And if there's not an index present there, we assume that it's 2. Okay, so the square root of 16 is going to be 4. Okay, now 8 to the 1/3 power, that is the cubed root of 8. Well, I know that 8 can be the same as 2 cubed. So as I simplify that, that is equal to 2. Now for C, 16, I'm going to do 16 to the square root power, takes care of the 1/2, and this is also to a -1 power because I got -1/2. So I'm going to simplify this and work it from the inside out. So -1, I remember that can bring things, I reciprocate it. So if I put this over 1, I'm going to get 1 over the square root of 16. And the square root of 16 is 4, so I get 1/4. My final example here, 8 to the -1/3 power. I know, again, I'm going to think that the cubed root of 8 to the -1 power. Well, the cubed root of 8 is 2 to the -1 power. Something to the -1 power, I reciprocate it, so I can get that this is 1/2. Okay. And our final example here in 7, I just want to write these in index form, so now going the other way. So again, if it's not written, I assume this is 2, so I can write this as 3 to the 1/2. Okay. In B, I can write this as 7 to the 1/3 power. Okay. In C, I'm going to break it down here. So first I want to write it so I'm not dealing with a fraction. So I'm going to do the 4th root of 7. But I know if I break it and bring it to the numerator, it's to the power of -1. And now I'm going to deal with my 4th root, and I'm going to get 7 to the -1/4 power. That concludes our notes for tonight, so make sure you highlight any questions you have and bring them to our next class.